Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 6 of our unit electromagnetic induction. Let's begin with today's session. In today's session we are going to discuss about the inductance. So let's begin. Inductor. What is inductor? We can say that a coil type of circuit element is called as an inductor. Many inductors are constructed as small solenoids. They can be considered as a small solenoids. Almost any coil or loop will act as an inductor. Whenever the current through an inductor changes, voltage is induced in the inductor that opposes this change. We are going to discuss this in detail. But first thing is how inductor look alike. We can consider that, let's suppose this is a symbol of an inductor. Generally this can be considered as an inductor, and that as capacitor has this symbol and that has been represented by C. Generally it is uh, we can say we use a symbol L to represent the inductor, such as resistor is having a symbol of R. So it is the conventional that we use a capital L to represent the inductor, and that can be represented as, if you take a wire and that wire is being converted, if this wire is being converted into circular loops, then this segment of the circular loops can be considered as an inductor. I hope this is clear. Is it clear? Great. Now the situation is that, let's suppose a current is passes through an inductor, changes, voltage would be induced in this current that opposes this changes. This phenomenon is known as the self inductance. So if it is the situation in which the current changing through a coil induces a current in the same coil, the induced current opposes the original applied current according to the Lenz's law that we understand. So this is the situation, something like this, that let's suppose inductor is there, and within this inductor, if current is changing, let's say di by dt, it is a rate of change of electric current. This will induce a current. Let me represent this I induced. So this I induce is induced, or we can say linked, we can say it's a linked with the same coil, then this is known as the self inductance. I hope this is clear. In the absence of any ferromagnetic in the space surrounding the coil, the total flux through the coil is proportional to the current I. And when we can say it's a proportional to the I, it is phi, which is directly proportional to the current I. If I remove the proportionality symbol, then I can say it's a phi is equals to L into I. If this coil has n number of turns, then I can write it's an n into phi, that should be is equals to L into I. Here L is called as the coefficient of self-inductance. It's a coefficient of self-inductance of the circuit. And this inductance L, this inductor L, depends on the shape and size of the loop, as well as on the magnetic properties of the surrounding medium. Unit of inductance is Henry. Yes. Now let's have a look that what is the EMF. It's an electromotive force of self-inductance. According to the Faraday's law, a variation in the current of the circuit causes an induced EMF. And when EMF is induced, thus differentiating the equation 1 with respect to time, we get it's a d by dt of n phi is equals to d by dt of L into I. So this could be represented as n into d phi by dt is equals to L di by dt. But this EMF was given as the E is equals to minus of n into d phi by dt. E is equals to minus of n into d phi by dt. So this could be represented as E is equals to minus of L into di by dt. Please remember this EMF is minus of L into di by dt, while when I represent this minus, this is according to the Lenz's law that it will oppose the one which will produce it. Please have this remember. And L di by dt, it is the magnitude of the cell because it behaves as an EMF. Does it clear? Are you sure? Are you? Great. So let's understood the situation. Let's understood the situation that when current in the coil increases, that means if di by dt is increasing, the induced EMF in the coil opposes the applied EMF, and so net EMF of the circuit can be given like this. So what we need to understand is, let's suppose di by dt is greater than 0, and if di by dt is greater than 0, this is the positive terminal of the battery, so current should be flowing through this. Now as this is changing, what was E? The EMF was E is equals to minus of L into di by dt. EMF E is equals to minus of L into di by dt. So what I need to do is, I need to replace this inductor. With a battery. Now what would be the polarity of this battery? How could I determine? So to determine this, what I am having an option is that if di by dt it is greater than 0, that means it is increasing. To oppose the one which will produce you need to decrease this current. To decrease this current, you need to replace it with a battery like this, because if you observe this battery very carefully, this is having a current in this direction which can oppose this current. So what you are supposed to do is, you are going to replace this inductor with battery like this, and the direction of current in this battery is something like this. I hope this is clear. Is it clear? Is it? Are you sure? Great. So this is the direction of the battery. Now let's take a different situation. Let's take the different situation. In this situation, let's assume that di by dt is decreasing, that the change in current is decreasing. If it is decreasing, then the situation will be something like this, that di by dt is increasing, so you are going to oppose the one which will produce you. Who is producing you? It's a decrease in di by dt. So what you are supposed to do is, you are just going to increase it. To increase it, you need to provide a current. You need to provide a current in the same direction. So you are going to replace this with a battery something like this, because the direction in this battery is current like this. Even in this situation, current is something like this. I hope you understand that both are representing the current in the same direction. Did you get this? Are you sure? Are you sure? So in short, if current in the coil decreases, the induced EMF in the coil favors the applied EMF, and so net EMF of the circuit would be E net equals to this first battery, this second battery, it would be an E plus E, which will be given as E plus L di by dt. And if it was the case that di by dt is increasing, then it will oppose the one, and to oppose the one, it would be an E minus E, which could be written as E net is equals to E minus of L di by dt. But the question is, if di by dt is 0, that means current passing through the coil is not changing, then EMF E would be equals to 0. So no need to think anything about this. Yes. So inductor can behave as a battery when it is having current which is keep on changing. If current is not going to change, then di by dt would be the same, and di by dt would be the same. That means this inductor cannot behave as an EMF. Have you got this? Any doubts, any issue up till now? Is there anything? Are you sure? Any doubts? Is there? Are you sure? Great. Let's look at the certain quick questions. What is it? So let's understood that whenever the current through the inductor changes, a voltage is induced in the inductor that opposes this change. This phenomenon is called as the self-inductance. Yes, this is the self-inductance that we understand. Let's take the second question. The unit of inductance. The unit of inductance. It's a Weber. It's an Henry. My mistake. Yes, we used to call it, this is phi is equals to L into I, and this L is equals to phi by I. Even it could be said as the Weber per ampere, but conventionally we are using an Henry only. Such as we have the resistance which is used to V by I. We have the resistance which we call as an R is equals to V by I, and we mostly not using it's a volt per ampere. No, we are not using it. We are using it's an ohm. So it is something like this that we always prefer to use Henry. There is nothing wrong in Weber per ampere, but we are using this. I hope this is clear. Is it clear? Is it clear? So let's discuss certain more things about this inductors. Let's say suppose this is the inductor, and when I say this is the inductor, cross sectional area of this inductor is A. N is the number density. While I say N is the number density, I mean this is the length of the conductor, and N it's the total number of turns. Capital N it's the total number of turns. L is the length of the conductor. It's the length of conductor. So small n is equals to capital N divided by L. Its a number density can be represented as total number of turns divide by length of the conductors. I hope this is clear. Is it clear? Is it clear? Are you sure? Great. So what I can write is it's a phi is equals to N into B into A. And while I write this capital N, I can write it's an N multiplied by L. This B could be written as it's a mu naught into Ni into area A. While writing this, it's a mu naught into N. This is N square multiplied by A multiplied by L multiplied by I. This is phi. Now I understand that we have started this with this. It's a phi directly proportional to the I, and when I write this, it's a phi is equals to L into I, or I should say it's a L is equals to phi by I. So this is the length of the conductor. So it's a phi by I, which is inductance as. Let me replace this L with small l so that it doesn't create any confusion. This is small l. Yes. So this phi by I, that would be equals to L, that would be written as mu naught into N square into A into length. Yes, this is the self inductance. This is the self inductance. A second relation could be written as mu naught into N square divided by L square. I'm just replacing this small n. It's a number density multiplied by A multiplied by L. So this L and this L could be gone. This is equals to mu naught into N square into A divided by L. I hope this is clear. This is self-inductance. This is self-inductance of coil. I hope this is clear. Is it clear? Is it clear? Are you sure? So, a thing which is to be noted is that we have a self-inductance which is something like this. It's a mu naught into N square into area into length. And one of other format is L is equals to mu naught into N square into A divided by length. So if area and length of solenoid is same, then L is directly proportional to the n square. And while I say small n, it's a number density. But if capital N is given, if capital N is given, then L, it's an inductance, is directly proportional to the capital N square divided by length. So in this case, it's an multiplied by L. In this case, it's a divide by L. Nothing to be confusion about. There should be no confusion in it. Yes, if I have been provided number density, I'm going to use this relation. I have been provided with the capital L, with the capital L, with the capital N, then I should go with the this relation. I should say relation number 2. It is as clear as that. Do you understand this? Do you understand this? Are you sure? Are you sure? Are you sure? Great. So, ready for the question? Are you ready for the question? Let's have a look. It says that a magnetic flux of 8 into 10 to the power minus 4 Weber is linked with the linked with each turn of a coil having 200 turns when current of 4 ampere is passing through it. Calculate the self-inductance. Calculate the self-inductance of coil. So let's check it out what all has been given. I have been provided a magnetic flux. I have been provided a magnetic flux, but this magnetic flux is linked with the each turn. So phi total should be written as n into phi due to each turn. So this is total number of turns. They are the 200 turns multiplied by phi due to each turn. It's an 8 into 10 to the power minus of 4. This is 2 8s are 16 into 10 square into 10 to the power minus of 4. This is equals to 16 into 10 to the power minus of 2. This is Weber. I hope this is clear. Now in this situation a current is passing. That current will be equals to 4 ampere. And when I say current of 4 ampere is passed through this, L could be written as phi by I. This phi is equals to 16 into 10 to the power minus 2 divided by current, that is of 4 ampere. This will give me a 4 into 10 to the power minus of 2 Henry. Have you got this? Have you? Do you understand this? Do you? Do you understand this? Are you sure? Are you sure? Do you understand? Do you understand this? Have you? Great. So ready for the next question? Are you ready? Great. Let's work for the next question. Initially, the wire having length L, the wire having length L converted to N1 turns of N1 turns of coil, N1 turns of coil having radius R. In next condition, same wire is being used to make a coil having having radius of r by 2. Find out ratio of self inductance in both the cases. So how will you do this? How will you do this? First, go through the data very carefully, and once you go through the data carefully, let me know what can be done. We have a wire that is having a length of L. Let's suppose this is a wire having length L, and it is converted to N1 turns of coil having a radius of R. So it's an L N1 multiplied by 2 pi R. It's a 1 ton would require a length of 2 pi R, and this is being converted into N1 number of turns. So it's an L is equals to N1 into 2 pi R. Now this is the first situation. Now in the second situation, the same wire is being used in radius r by 2. So what I can write, it's an L, this will be the same, it's an N2 multiplied by 2 pi r by 2. But that I understand the same wire is being used, so I can compare this L. So what I can have, it's an N1 into 2 pi r, that should be is equals to N2 multiplied by 2 pi into r by 2. This could be gone, this could be gone, and this pi r could be gone. So this is N2, it's equals to 2 and 1. So next time it has made a double number of turns than the previous one. I hope this is clear. Is it clear? So what would be the situation? The situation would be you are having a number of turns. You are having a number of turns. N1 is there, N2 is there, and what do you need to find out? You need to find out the ratio of the self inductances. How will you do this? How will you do this? So my self inductance is that I know its a master formula is mu naught into n square into a divided by L. Yes, this is the self inductance formula. So let's take a ratio of this. This is a small L. Let's take a ratio of this. It's an L1, it's to L2. Let's take this L1 is to L2. This mu naught will be a cancelled out. This N1 square into A1 divide by length multiplied by N2 square into A2 into L, because the length of the inductor was same. It's the length of the inductor was same. Yes, great. Now it's an L1 is to L2. So this is equals to N1 square divided by N2 square multiplied by A1 divided by A2. This is N1 square divided by N2 could be replaced by 2N1. So it's a square of this, it's a 4N1 square multiplied by area 1. Area 1 was pi into R square divided by area 2, it's a pi into R by 2 whole square. So this N1 square, this N1 square gone, this gone, it's N1 by 4 multiplied by 4R square divided by R square. This has gone, so this is 1 is to 1, this is L1 is to L2. I hope this is clear. Is it clear? Is it clear? So can you do this? Can it be done? Can it be? Are you sure? Can you do this? Can it be? Great. Let's work for the second category of questions. It will say that let's suppose an inductor is there, and this inductor is something like this. This inductor having an inductance of, let's say, 5 millihenry. Here a current of 3 ampere is passing, but this is not changing. Di by dt is equals to 0. What would be the EMF? I have been asked that. Find EMF E linked to the inductor. So when I say di by dt is equals to 0, it's E is equals to minus of L di by dt. But as di by dt is 0, this cannot behave as a cell or as an EMF. I hope this is clear. Now let's take the same example. Let's take the same example with certain variation. The variations will be that we have again taken the same inductor. Well, I say same inductor, it is a 5 millihenry only. The current is even the same, it's a 3 ampere. But now in this time, di by dt is equals to 2 into 10 to the power 3 ampere per second. It is increasing. I hope this is clear. It is increasing. Find out. Find out EMF. I hope you understand now the symbols. Yes, this is the sign for the increasing, and the downward arrow. Downward arrow will represent that it is decreasing. So what I need to do is I can replace my inductor as a cell. How? First you need to do one thing, that you need to convert your inductor to a cell, and first task would be to find out the magnitude. Let's have it. To find out the magnitude, it could be written as E is equals to L di by dt. This could be written as 5 into milli, it's a 10 to the power minus of 3 multiplied by di by dt, that is equals to 2 into 10 to the power plus 3. This plus 3 minus 3 would be gone, and this will be the 10 volt. I hope this is clear. This is 10 volt. Now our first task is over. Now let's work for the second task. What you need to do is you need to find out the polarity of the battery, that where it would be having a positive terminal, where it would be having a negative terminal. If you observe the circuit carefully, the current is flowing through in this direction. So if I look at the backward of the circuit, it would be something like this, that current has been passed through this, and it would be something like this. Yes, and I have shown only this segment. So this is the battery, or this is the master cell. I could say this, that this could be the master cell, and this master cell has provided the current that is equals to 3 ampere. So what I need to do is I need to flow a current which will oppose it. Why to oppose it? Because this is increasing. If it is increasing, what I want that it should decrease. How to decrease it? By converting a battery of negative polarity. Now this is the I induced, this is the direction of I induced, and this is the cell of 10 volt. I hope this is clear. This I induced will flow in the opposite direction to the I, and my task has been done. You did it, great job. I hope this is clear. Is it clear? Is it? Do you understand this? Have you got this? Have you? Do you understand this? Are you sure? So can we do the questions based on this principle? This is one of the favorite questions of examiners. Yes, in both the segments, in medical as well as engineering examinations. So please look at this very carefully, and this play a vital role. Let's suppose the situation is something like this. This is a battery of 10 volt. This is a resistance of, let's say it's a 10 ohm. This is a resistance of 20 ohm. This is the inductance of, let's say, 5 millihenry. The current is di by dt, which is equals to, let's say, 3 into 10 to the power 3 ampere per second. It is decreasing. Yes, let's say this is potential, this is point A, this is point B, and current is flowing in this direction with a value of I is equals to 2 ampere. What I need to find out? I need to find out VAB. How will I do this? This is the situation. I have been asked VAB, what will I do? Always do one thing. Always convert your inductor into a battery if possible. So why if possible? Because if di by dt is not going to change, that means it is not possible to convert this into a battery. So if this is being changed, look at this. In our case, it is being changed. In our case, it is being changed, and when it is being changed, I need to convert this to a battery. So when I need to convert this as a battery, what I need to do is I need to first find out the magnitude. So let's first calculate the magnitude of this battery. That will be the L di by dt. This is 5 into 10 to the power minus of 3 multiplied by 3 into 10 to the power plus 3. This plus 3 minus 3 has gone, and this is equals to 15 volt. Yes, great. Now one more thing, as this is decreasing, this change is decreasing, so what you need to do, you need to do something like that. It will increase it. Why? Because you are going to oppose the one which will produce it. Who is producing you this decreasing change? So what you are supposed to do is, you are just going to increase it. To increase it, you need to arrange a battery in a direction such as that your current will flow in this. It is something like this. So let me redraw the circuit. The situation is that this is a 20 ohm. This is a battery that was made up from the inductor. This is the another battery. This is 10 and this is B. Yes, so this is A, this is B. This is a battery of inductor. It's a 15 volt. This is 10 volt. This is 20 ohm and this is 10 ohm. And the current that is of 2 ampere. So now let's just VAB. Let's just calculate. It's a VAB. Now it's a simple question of KVL. It's a Kirchhoff's voltage law. What we are supposed to do is, if we are moving in the same direction as current is passing, we are just going to add this all the IR. And when I stuck with the battery terminal, whichever the battery terminal I will stuck with, I'm going to write this polarity. If I have been collide with the positive terminal, I'm going to write it positive. If I'm going to collide with the negative terminal, I'm going to write it as a negative. So I'm going in this direction. So first I'm moving in the same direction as current is moving. It's a 22. This is 40. Next battery of negative terminal is there. This is minus of 15. Next battery of positive terminal, it's there. It's a plus 10 plus this is 10 of, this is 2 ampere, this is plus 20. So this will be the 40 plus 20, 60, 60 plus 10, 70, 70 minus 15. It's a 55 volt. This would be the potential difference across AB. It's a VAB. I hope this is clear. Is it clear? Is it? Do you understand this? Are you sure? Are you sure? Ready to do one more question? Are you? Let's have a look. Let's suppose a battery is there, a resistance is there, inductor is there, again a resistor and a battery, something like this. This is A, this is B. Let's say this is 10 volt, this is 2 ohm, this is, let's change the inductor, its value would be 3 millihenry, and this is 4 into 10 to the power 3 ampere per second. It is increasing. This is 4 ohm, this is of 12 volt, and current is flowing in this direction. It's I is equals to 3 ampere. What is the question? Question is find VAB. So what I need to find, I need to find out VAB. How will I do this? First task is to convert this inductance into a battery. How will I do this? Simply write down this. It's an E. that is equals to L di by dt. L is the 3 millihenry, it's a 3 into 10 to the power minus 3. Di by dt, it's a 4 into 10 to the power 3. This plus 3, this minus 3 has gone, and this is 12 volt. Now as this is increasing, I need to replace it so that it can decrease it. How to decrease it? By creating a battery, by creating a cell in the reverse polarity. How to do this? It is something like this. I hope this is clear. So replace this inductor such like this, and you will definitely do it. I hope this is clear. Is it clear? Is it any doubts? Let's redraw the circuit. Then it will look like that. This was the battery terminal, then it was the resistance, then again it was the battery. That was initially it was the inductor, next battery, and next again it's a 12 volt of battery. This is A, this is B, this is 12 volt, this is 4 ohm, this is again a battery of 12 volt, this is 2 ohm, this is 10 volt, and the current is flowing in this direction, the current of 3 ampere. What I want a VAB, but for initial stage, what you can do is you can find out the VBA and multiply it with minus of 1. This will because we generally it's a human tendency to write it in a positive manner than in the negative manner. So if you wish, you can find it out VBA, because current is flowing from B to A. If you want this, you can do this. Otherwise you can even write it from A to B. So let's write VBA. First, it's a positive terminal of the battery, it's a plus 12, plus 4 into 3, it's a again 12, again positive terminal, it's a 12, again 3 2s are 6, now it's a negative terminal, it's a minus of 10. So this is equals to 12 plus 12 plus 12, it's a 12 3s are 36, plus 6, it's a 42, 42 minus 10, it's a 32. But this is VBA. What I have been asked? I have been asked VAB. This VAB could be written as minus of 32 volt. You get this? I hope this is clear. Is it clear? Is it any doubts up till now? Is there anything? Do you have any doubts? Do you have any doubts? Is there anything? Is there? No? Now let's discuss about the magnetic energy stored in a solenoid in terms of the magnetic field, area, and length. Let's discuss about it. So when the current grows through an inductor, the induced EMF opposes its growth, and it's such as it has to do some work. So when the current in the circuit has attained its maximum value, the induced EMF vanishes, and as such the current has to do work now. So current now cannot do anything. Now the total amount of work done by the current in attaining its maximum value is sorted in the inductor in the form of its magnetic energy. So when the circuit is broken, when I say when the circuit is broken, I mean when the switch is open, the current stops following in it, and this stored up energy is released, and it maintains the flow of current for some time more. If you go through it one more time, this is what we understood as an electrical inertia. Have you remembered the word inertia? Have you? What do you understand by the inertia? Yes, it is resist to change. When and when we used to say it's a inertia, that means we understand that it is not accepting it that it is going to be changed. That is what we call as an inertia. So when the circuit is broken, when we switch off the circuit, the current should stop. The current should stop in the situation. But when this happens, what inductor is supposed to do, that it should be continued. It should be continued, and so that it will supply an energy for a very short period of time. I hope you understand this. So let's suppose that the current flowing through the circuit at any instant of time t will be the I, and the rate of growth of current at that time, will be equals to di by dt, and induced emf set up in the circuit is E. So according to the law of Faraday, this E is equals to L di by dt. So we have an EMF. Now let's find out the work done. Work done by the current in a time dt, that can be considered as dw is equals to ei dt. It's a vi dt. So if I understood L, it is just L di by dt multiplied by I dt. Or if I cancel this dt and dt, this is equals to dw, that is equals to Li di. Now let's integrate this. So total work done by the current in increasing from 0 to its maximum value I, that could be considered as this is equals to 0 to dw, this is equals to 0 to I Li di. This integration of dw will give me the work done. This is equals to L integration of I di, and when I integrate this I di, this is equals to Li square by 2, this is equals to half Li square. This is the work done. This work done is equals to half Li square. So so it is the amount of work which is stored in the circuit in the form of its magnetic energy. So if you have remember the energy stored in the capacitor, have you remembered it? Have you remembered it? The energy stored in the capacitor was something like this. It's a q square by 2c, or we used to have it as an half cv square, or even we can have it as a q into v by 2. So this form of energies were there when we used to charge the capacitor and we make a work done in the capacitor. That amount of energy was in the form of electrical energy. Now here all the setup energy will be in the form of a magnetic energy. There is a large difference between these two, but they have a certain similarities between their working pattern. I hope you understand this. Great. So let's understood that, let's suppose we have a long cylindrical solenoid, and we understand that magnetic field of the solenoid is B is equals to mu naught into Ni, where N is the number of turns per unit length. And we also understand that inductance of the solenoid could be written as it is mu naught into n square into a into L. So if I find it out, the magnetic energy stored in the solenoid, if I find out magnetic energy stored in the solenoid, this could be written as half into mu naught into n square into al divided by b square divided by mu naught square n square. And this is where we are going to land on the 1 by 2 b square al by mu naught. So if I talk about the energy density, which is equals to total energy divided by volume, then this total energy divided by volume could be written as b square by 2 mu naught. In the energy density, when I talk about the energy density in the capacitor, when we said its energy density in the capacitor, it was just half epsilon naught into E square. This is electric field. Now in this situation, it is equals to B square by 2 mu naught. I hope this is clear. Does it clear? Are you sure? Are you sure? Great. So now first let's look at the certain quick questions, and then we will move to the numericals. First, the total amount of work done by the current in attaining its maximum value, stored in the inductor in the form of it's stored in the form of its magnetic energy. Let's look at the second question. It says that the total work done by the current in increasing from 0 to its maximum value, this work done will be equals to half Li square. This is the work done. This is the work done which we say that's in work done is equals to half Li square. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Great. Now let's look at the second question. Let's say two coils are there. Two coils having self inductance. Having self inductance. Let's call L1 it's equals to 4 millihenry, and and L2 is equals to 8 millihenry. Let's suppose understood that current in both the coils are increasing at same rate. If power in both the coils, if power in both the coils are same, if power in both the coils are same, find find first the ratio of current in the inductor, and second it's a ratio of potential difference. It's a ratio of potential difference. And the third, it is the ratio of energy stored. It's a ratio of energy stored. So go through the data once and tell me what do you understand. So they are having two coils and the self inductances have been given. It's an L1 and L2 as given, and the current in both the coils are increasing at the same rate. So let me summarize this, that L1 is given, which is equals to 4 millihenry. L2 second self inductance is given, it's an 8 millihenry, and they said that current is increasing in both the coils with same rate. It's a di by dt1, it's a di by dt2. Okay, great. Next, if power in both the cases are same, so they said that power P1 is equals to power P2. Okay, great. What I need to find, it's a rate of current. It's a rate of current in the inductor. So it's a basically ratio of current in the inductor. How shall I find it out? What should I do it? So let's have a look, that what we are supposed to do is that what I can understand is this P1, it's a V1 I1. This is equals to V2 I2. When I say V1 I1 is equals to V2 I2, we understand that this could be V1 could be written as L1 di by dt multiplied by I1. This is equals to L2 di by dt into I2. When I said that di by dt are equal, that means this two has been equal, and when this is equal, this is equals to L1 I1, this is equals to L2 I2. So when I take a ratio, it's an I1 is to I2, I1 is to I2, this is equals to L2 is to L1. So this L2 will be equals to 8 into 10 to the power minus of 3, while L1 would be equals to 4 into 10 to the power minus of 3. This has gone, and this I1 is to I2, which is equals to 2. I hope this is clear. Is it clear? Is it clear? Are you sure? Great. Now let's work for the second question. The second question says that find out the ratio of the potential differences. So for the second question, it's a V1 is to V2, which should be L1 di by dt divided by L2 di by dt. Now, as they said, di by dt are the same, and when di by dt is the same, it's a ratio of L1 is to L2. While L1 is the 4 millihenry, This is 4 into 10 to the power minus 3. L2, it's a 8 millihenry. It's a 8 into 10 to the power minus 3. This has gone, and this is equals to half. Again, this is half. Great. Now, the third part. Third part of the question is, it's a ratio of the energy stored. So let's do it. So the ratio, it's a work done 1, it's to work done 2, it's a half L1 I1 square divided by half L2 I2 square. This half and half has been gone, and I have been left with the L1 is to L2 multiplied by I1 is to I2 whole square. So when I say it's an L1 is to L2, this is 4 is to 8 multiplied by I2 is to I1. It's this is 2 square. So this is 4 into 4 divided by 8. It's a 4 twos and 2 twos. So this is equals to 2, having no units left with it. I hope this is clear. Is it clear? Is it clear? Are you sure? Are you sure? Do you understand this completely? Have you? Have you understood this? Are you sure? Do you understood this? Have you? Have you? Great. Now let's discuss one logical question. A very good question, in fact. Let's first look at this and try to understand what the situation is. This is the situation that we have two bulbs, while one of the bulbs, this is the situation, yes. We have two bulbs. This is bulb 1, this is bulb 2. This bulb 1 has been connected with the resistance R, and this bulb 2 has been connected with inductance L. And these two circuits have been connected with the EMF. As you can see, these two branches are parallel with each other, and it has been connected with the key. Now the question is, discuss the behavior of the circuit. Discuss the behavior of the circuit when switch is closed to the steady state. So I need to discuss this behavior because the certain logical questions can be asked, and previous track record of the competitive examination says that it has been asked. So let's just discuss this, that how this circuit will behave. So when I close the switch, when I say at t is equals to 0, this inductor will behave as an open switch, so it means bulb 1 will be on, because as if you understand that this is open, the current would be having only one path, because this path is not available for it. So bulb 1 would be on, and bulb B2 will be the off. Now what happens? Let's suppose ki at we have discussed about the at t is equals to 0. Now as time passes, and let's we have achieved steady state. We have achieved a steady state. Inductor will behave as close switch. So when inductor will behave as a close switch, situation will be something like this, that this was the resistance, this was the bulb 1. Now here inductor was there, now it is only the bulb, because inductor has been replaced. So this is the situation. At this place inductor was there, and I have replaced this inductor by a wire. This was the R, this was the B1, this was the B2, and here initially inductor was there, and this is the EMF. So as time passes, we have achieved the steady state. Inductor will behave as a closed switch. So in this situation, bulb B1 will be on, bulb B2 will be on. Now tell me, if someone asks me, what could you discuss? What is your observation about their brightness? Which bulb is having an higher brightness? What do you think? What do you think for this? So when I discuss their brightness, I must understand that this path is having a resistance R, but this path is not having the path resistance this. So brightness of bulb B2 will be higher as compared to brightness of bulb B1. I hope this is clear. So this is the instant when we have reached the steady state. Question was about this only, but let's keep this question continue, and let's suppose discuss that now if switch is opened. Now if switch is open, so the situation will be something like this, that the situation was, this was the resistance and initially this was the bulb. It it was inductor, this is bulb B2, this is the, and now it has been opened, something like this. So this is inductor which was at steady state, and when it was at steady state it can behave as a closed path, that we understand. This is B2, this is B1, this is R. So now if switch is open, that it has been open, what happens? So if switch is open, at that instant inductor starts behaving inductor starts behaving as a temporary source of energy, because it is having a magnetic form of energy. And this is what we discussed, that this is what we call as an electrical inertia, that inductor wishes that whatever happens in the previous time should be move on in this time too. So previously someone was there, this EMF E was there to provide us the supply. Now we have opened the switch, so if we have opened the switch, inductor will behave itself as a source of energy, and it will keep on glowing B1 and B2. And after a certain time brightness of B1 and B2 will be equal, because now they can behave in a series circuit. Yes, if you observe that inductor is a source of energy and it is just like the battery, then this B1 and B2 will be in the series circuit, and when they are in series circuit, current would be the same. If current would be the same, their brightness will be the same. So and eventually they will die out, because basically it's an inductor. It is not a battery, it just try to behave as a battery, it is not a battery itself. So I hope you understand it. It can behave as a temporary source of energy, it cannot provide that amount of power that any cell can give. I hope this is clear. But at that instant of time, if you want to see at that momentarily instant, it is definitely behave as a source of energy, that I am there to provide you the supply. It is something like that. I hope this is clear. Very interesting. Don't you get this? Are you sure? Are you sure? Great. So let's wind up this session over here. This was all about the induction. Very probably very lengthier section, but it was required, because if I break this session, it probably could not deliver the way it was or it should be. I hope you understand it, but this is very very important aspect, and this is very important topic of the class 12, because here it is only the one segment where we studied the induction in a proper manner, and now onwards we are going to use inductor as a component only. So this is having a very high weightage when we consider this topic according to the competitive examinations. Please go through this very carefully. Please practice a lot this kind of question. This will help us, this will save us. Thank you, have a good day, take care, bye bye. Let's look at the mutual inductance. Mutual inductance, let's understood what it is. When we say it's a mutual inductance, we can say that it is possible for the magnetic field of one coil to produce and induce current in a second coil. Up till now we were discussing and we were studying about the self inductance. The situation was a current has been passed through one of the coil, and inductance has been linked with that coil, with the same coil. Now in this situation it is something different would happen. That let's suppose if I close this key, and as this is connected with the battery, so due to this battery a current would be completed, a path has been completed and current will be flowed through this. But as if I change the current by somehow, then there is something, induced current has been linked to the second coil. This is what we call as a cell mutual inductance. The coils are connected indirectly through the magnetic flux, because it is basically a magnetic flux. It's a phi is equals to b dot a, while the b is the magnetic field, and field is always a kind of energy, so that can propagate anywhere. And due to this magnetic flux current will be induced in this coil. This effect is known as the mutual inductance. Now let's study this analytically, that what would happen. So we are just considering mutual inductance of two, long solenoids. So what we have supposed done is that we have considered two long coaxial solenoids. One of them is the S1 and another is the S2, with S2 wound over S1, and let's suppose this length of the each solenoid is taken as the L, and R1 and R2 are the radius of inner and outer solenoids. While I say area would be equals to pi into r square, which would be the area of the solenoid, and n1 and n2 are the respective number of turns in the two solenoids. So these are the notations I'm going to use. Yes, we have kept two solenoids, one over the other, and these two are the coaxial solenoids. N1 and N2 are the number of turns in the two solenoids. First, what we are supposed to do is we will pass a time varying current I2 through S2, and due to this the magnetic field will set up inside an S2 due to this I2, and that magnetic field will be is equals to mu naught into N2 into I2, where when I say N2, it's N2 is the N2 by L. It is a number of turns per unit length of S2. Yes, we always call this N, which is equals to N by L, which is equals to number of turns, per unit length. It is the small n, it's a number of turns per unit length. So total magnetic flux that is linked with the inner solenoid S1 is phi 1 is equals to B2 into A into N1, and this is equals to mu naught into N2 I2 into A into N1. Now mutual inductance, when I say it's a mutual inductance of coil 1 with respect to coil 2, that is what we call as an M12, which is equals to phi 1 divided by I2, that is equals to mu naught into N2 into A into N1. If I want to replace this, N2, it's a number of turns per unit length, then this could be written as mu naught into N1 into N2 into A divided by L. So this is one of the situation when current has been passed through the solenoid 2 and the mutual inductance has been linked with the solenoid 1. Now let's do the completely reverse situation. Now let's consider that the flux is going to link with the outer solenoid S2. due to the current I2 in the inner solenoid S1. And when this happens, the field B1 due to I1 is constant inside S1 but 0 in the annular region between the two solenoids. Hence, magnetic field will be equals to mu naught into N1 into I1, where I say in N it's a number of turns per unit length through an S1. So the total flux when this magnetic field is varying, and due to this the total flux linked with the outer solenoid S2 is what we call as in phi 2 is equals to B1 into A into N2, and this is equals to, when I replace the value of B1, it's a mu naught into N1 into I1 into A into N2. This is number of turns per unit length, so let's just replace it. So it will give me a mu naught into N1 into N2 into A into I1 divide by L. Now what is flux? When I say mutual inductance, sorry, it's an M is equals to phi by I am doing the same thing. So this is M21, this is M21, which is equals to phi 2 by I1, and when I say it's an phi 2 by I1, that would be mu naught N1 N2 A upon L. So if you look at this M21, and if you look at this M12, look at this, it's an M12, it's a mu naught N1 N2 area divided by length. When I talk about the M21, it's a mu naught N1 N2 A divided by L. So from this we can say that M12 and M21 are the same. That means no need to write out M12 or M21. We can call it as an M. It's a mutual inductance. Thus the mutual inductance of two coil is the property of the combination. It is not an individual one. It is just the property of these two coils when they are connected. It does not matter which one of them functions as the primary or secondary. So this is not certain kind of primary coil or secondary coil. No, this is just that they are just the property of this combination, or we can say this is the property of this pairs. So this fact is known as a reciprocity theorem. And this mutual inductance, now I will not write it's a mu M12 or M21. Now what I'm going to write is it's an M is equals to mu naught into number of turns of the first coil multiplied by number of turns of the second coil multiplied by cross sectional area divided by L. Or rather, if I can replace it, it would be a mu naught into N1 into N2 into A into L. So if you have given number of turns per unit length, this length is directly proportional to the mutual inductance. If they have given N1 and N2, it's a number of turns only, then this is divided by L. Please keep this in mind. This is equals to mu naught N1 N2 pi into R1 square into L. I hope this is clear. Is it clear? Is it? Are you sure? Any doubts up till now? Is there anything? Is there anything? Are you sure? Great. Let's look at certain quick questions. The first question says that it is possible for the magnetic field of one coil to produce and induce current in a second coil. This phenomenon is known as, yes, this is mutual inductance, that current is going to be passed through one of the coil, and due to this current, mutual inductance, or we should say inductance, has been linked to the other coil. This is the mutual inductance. Let's look at the second question. Reciprocated theorem is fact from the blank concept. Yes, it is the concept of mutual inductance, that no one behaves as a primary or no one can behave as a secondary. It is just the property, of this two combination that will work for us. I hope this is clear. Is it clear? Is it? Are you sure? Any doubts? Is there anything? Is there? Are you sure? Great. Now let's discuss something, that when I say M, that is equals to mu naught into N1 into N2 into area divided by L. When I say this, I must I must consider area of lowest radius solenoid. So it is always an we could say this, that it is the always an area, it is always an area of the minimum possible radius. Yes, it is always the intercepting area, it is always the intercepting area, or I should say this, the area which is minimum one. I need to check this. One more thing, when I say it's an m is equals to phi, or I should say it's a phi is equals to m by m into I, this is something like phi is directly proportional to the I, and when I replace this with a constant, this is phi is equals to m into I. So mutual inductance can be also calculated from this fact that m is equals to phi divided by I. M is equals to phi by I, while flux phi is the flux and I is the current that has been passed through any one of the coil. I hope this is clear. Is it clear? Is it clear? Are you sure? Ready for the question? Are you? Let's have a look. Let's suppose the question is that two coaxial solenoids are wound one over other such that such that one of the solenoid such that one of the solenoid is having 300 turns and other has 400 tons. If cross sectional area of this solenoid is A is equals to 10 centimeter square and length is length is 20 centimeter, find mutual inductance. I hope this is clear. So let's find it out. What data has been given? They say two coaxial solenoids are there. And they have been arranged such that one of them is having a number of turns of 300. It's n1 equals to, let's call it 300 turns, and 2 is equals to, let's call it, it's a 400 tons. And if cross sectional area of this solenoids is A is equals to 10 centimeter square and the length of the solenoid is 20 centimeter. What else that has been given? No? Great. Now let's find out the mutual inductance. So I am already given n1 and n2. Now I need to do, it's an m is equals to mu naught into n1 into n2 into area divided by length L. While I say so, this is equals to mu naught, that is equals to, let's keep it this at this point of time, mu naught itself multiplied by 300, which is 3 into 10 to the power 2, multiplied by 400, which is a 4 into 10 to the power 2, multiplied by area, it's a 10 centimeter square. So convert this to the meter square, it's a 10 to the power minus of 4, and length, it's a 20 centimeter, it's a 20 into 10 to the power minus of 2. So mu naught, it's a 4 pi into 10 to the power minus 7, multiplied by, this is 2, this is 2, 4, this is 10, it's a 10 to the power 5, multiplied by 10 to the power minus 4, this is 3 4s are 12, divide by 20 into 10 to the power minus of 2. So if I replace this, this is 2.4 pi multiplied by 10 to the power minus of 4 Henry. Yes, it is it contains the same unit as that has been contained by the self inductance Henry, denoted by small h. I hope this is clear. Is it clear? Is it? Are you sure? Okay, great. Now let's write down the relation between mutual inductance and and self inductance. When I want to find out the relation between mutual inductance and self inductance, I am sure you have derived this in your theory classes. It is M, which is directly proportional to the root of L1 L2. If I replace this proportionality with constant, that is K, that is equals to root of L1 L2, so I could say it's a K is equals to M divide by root of L1 L2. But this is theoretical approximation. This is theoretical approximation, or I should say it's a theoretical assumption. In practical situation, in practical situations, this K should be less than or equals to M divided by root of L1 L2, where K is called as the coefficient. This is known as coefficient of coupling. So if they understood an ideal situation or theoretical approximation, then this is equals to this coefficient of coupling. It would be equals to M divided by root of L1 L2. And if they we understood a practical situation, because it is not possible that self inductance due to both can be linked as a mutual inductance 100%, and there would be no energy losses. When I say theoretical, we understood that let's suppose there is no energy loss, and whatever the inductance has been induced in first has been linked with the second one. So this is just the theoretical approximation, or we can say assumption. This is not the case when we deal with the practical life problem. So when we does it with in a practical situation, there is always an energy loss, because whatever you are going to do is you are going to, or you are supposed to do in the environment and with presence of atmosphere, so there must be energy losses would be there. And when if I need to consider this coefficient of coupling would be less than m upon under root of L1 L2. So this is the correct relation, that it should be less than or equals to maximum. It would be an equal to, less than it would be, it could be lesser than this. I hope this is clear. Is it clear? So please keep this in mind and please note it down. Let's work for the question. Let's suppose it says that mutual inductance of two coils, mutual inductance of two coils which are having self inductance of 18 millihenry and 8 millihenry, having coefficient of coupling, having coefficient of coupling point 0.5 is. So if I can write it's a coefficient of coupling is already 0.5, so I should write it's a K is equals to M upon under root of L1 L2. This is 0.5, so I could write it's a 5 by 10. This is equals to, I need to find out the mutual inductance. This is 18 millihenry and 8 millihenry. This is 18 into 8 into 10 to the power minus of 3. So while I do this, this is equals to 1 by 2 is equals to M. It's a 18 8 is 144, 144, it's a 12 into 10 to the power minus 3. So this M is equals to 12 by 2. This is equals to 6 into 10 to the power minus of 3 Henry. Yes, it's a 6 millihenry. I hope you understood this. Have you understood this? Have you? Are you sure? Are you sure? Great. So Shall we move to the next pattern? Yes, let's have a look. Now we are going to discuss about the combination. It's a combinations of inductor. So as we have a series combination and parallel combination of resistors, in a same way we have the combination of resistance, we have a series combinations of inductor and the parallel combinations of an inductor. So let's begin first with the series combination. When I connect inductors in series combination, so it is something like this, that let's suppose this is first inductor and this is second inductor. Let's say suppose a current has been passed through this and the di by dt is the change of this. So this is, let's call it L1, this is L2. Let's suppose this is V and this is V2. So when they are connected in series, what I could write, it's a V total, that would be equals to V1 plus V2. When I call it, it's a V total, this is equals to L equivalent of di by dt. This is equals to L1 into di by dt plus L2 into di by dt. So when I write this, it is di by dt, di by dt, and di by dt. This has been lost, and I have been left with the L equivalent, that is equals to L1 plus L2. Let's suppose in a generalized term L3 plus L4 up to Ln. While I have derived this, I have not used a property of mutual inductance up till now. In this situation, I hope, do you understand this? Do you understand this? That in this situation, I have not used anywhere the effect of mutual inductance. I hope this is clear. Is it clear? Is it clear? Are you sure? Great. Now, let's work for the parallel combination. It's a parallel combination of inductor. So this is the situation. This is L1, this is L2. Now let's suppose the situation is that total current I has been passed through this, and when this current I has been passed through this, a current is being divided into these two segments, that I is equals to I1 plus I2. So when this has been divided, this could be written as I is equals to I1 plus I2. Let's differentiate this with respect to time. This is equals to d by dt of I. This is equals to d by dt of I1 plus d by dt of I2. So in this situation, I am having a master relation which is equals to L di by dt. So this di by dt would be equals to V divided by L. So when I write this, it's a di by dt. This is equals to V divided by L equivalent. This is equals to V divided by L1, because the potential drop will remain the same as they are connected in parallel. V by L1 plus V by L2. This V has gone, and this is equals to 1 by L equivalent. That is equals to 1 by L1 plus 1 by L2 plus 1 by L3 up to 1 by Ln. This is the equivalent. So I understand that it is the same relation that I have received, or that I was getting when we used to deal with this resistors. Yes, so we don't need to do anything extra. It is the same thing. We understand the how they are connected and what that can be done, when what uh, tricks and techniques can be used to resolve the networks. Let's have a look. Let's take a very few questions. because we already know how to deal with the series and parallel combination, and this is not new for us. So let's have a look. Let's suppose the situation is this is first, this is second, this is third, and this is fourth. This is of 4 millihenry, 2 millihenry, 3 millihenry, and 4 millihenry. So this is the A end, this is the B end. So L equivalent for this, it's a 4 plus 2 plus 3 plus 4. It's a 4 plus 4, 8, 8 plus 2, 10, 10 plus 3, it's a 13 millihenry. Yes, have you done this? Got this? Great. Let's work for the second question. Let's suppose the situation is something like this: first, second, third, and let's suppose it has been connected with this. So the situation is this is point A, this is point B. You need to find out the L equivalent. So if this is A, this is A, this must be A. If this is A, this must be A. If this is B, this must be B. So let's just resolve it. Let's just resolve it. So what we are supposed to do is that this is A, this is B, and let's call this every inductor as an L, L, and L. So this A to B, this could be written as this is in parallel, this is A to B. So this has drawn. Now this B to A, this could be drawn like this, and this A to B, this could be drawn like this. So this is L, this is L, this is L, and this L equivalent could be written as L by 3 Henry. Have you got this? This L equivalent that should be is equals to L by 3 Henry. Have you done this? Have you done this? Are you sure? Any doubts? Is there anything? Is there anything? Are you sure? Are you sure? Any doubts? Is there anything? Is there anything? No? So now let's discuss the effect of mutual inductance when they are connected in series or parallel. So effects of mutual inductance on combinations of the inductors. So let's understood the situation very simply, that let's suppose this is first inductor and this is second inductor. If this one is the first inductor, this one is the second inductor, and let's suppose this is L1, this is L2, a current has been passed through this, so it is obvious that current is passed through the second inductor as well in the same fashion. So through both the current is going in the same fashion, and when the current is going in the same fashion, what I can write is that let's suppose this is the V1 and this is the V2. So when I write it's a V1, I should write it's an V1 that should be is equals to L1 into di by dt plus effect of mutual inductance, it is M di by dt. Now potential drop across second coil, I mean second inductor, V2, that would be equals to L2 into di by dt plus M di by dt. I hope this is clear. Now when the situation is that this is the one of the end, this is the another end, this VAB, this is equals to V1 plus V2. So when this VAB is equals to V1 plus V2, this is what we call as an L1 plus L2 into di by dt plus it's a 2m into di by dt. I hope this is clear. Is it clear? So this is VAB. This is VAB. So from this L effective could be written as it's an L1 plus L2 plus 2M. So in short, what I need to do is that if current is passing through this in the positive x direction, current is passing through this in positive x direction, I need to add their mutual inductive effect. That mutual inductance has been linked with this, and mutual inductance has been linked with this. This effect is going to be added. Have you got this? Have you? Are you sure? Great. Now let's look one of the very critical question, that how will I deal with this? This is first coil, and let's say this is the second coil. This is the situation. So what I need to do is, current has been passed through this. This is L1, this is L2. So in this situation, look at this. Does they are connected in series? Do they are connected in series? Yes, no. My answer would be yes, definitely they are connected in series. Now, if they are connected in series, then what would be the situation is that current in this and current in this coil both are in the opposite direction. I hope you understand this. Have you? So when you understand this, when you understood this, you must understand that this L effective could be written as L1 plus L2 minus of 2M. Why? Because both this mutual inductance are in opposite sense to their self inductance. So if you write this V1, you must write this as an L1 di by dt minus of M di by dt. Why minus? Because in this coil current is passed through this, and mutual inductance has been linked due to current in L2. Same way when you write a V2, that would be equals to L2 into di by dt minus of M di by dt. So when current pass through them, is in an opposite direction, their mutual inductance will oppose their self inductance. Please do remember this. Have you got this? Have you got this? Are you sure? Are you sure? Great. Let's work for one of the question. This will help us to understand it probably in a more effective way. So the question says that two identical coils are connected in series in two different way. Find out their L effective. So the first situation is, it is something like this. This is something like this. This is A, this is B, this is L, this is L. So the situation is this L effective and current may be passing through this. This is equals to L1 plus L2 plus 2M. Assume that K is equals to 1. That means sometimes they will ask that they are perfectly coupled. Yes, when they say they are perfectly coupled, that means you are going to assume that K is equals to 1. So this is L1 plus L2 plus 2M, this is 2L plus 2M, but let's replace the value of M as well. So to replace the M, I could have a relation that K is equals to M divided by root of L1 L2. When K is equals to 1, this is equals to M divided by root of L square, and when they are root of L square, this M is equals to L. This is equals to 2L plus 2L, which is equals to, it's a 4L. This is the L effective. Which we call as an L effective is equals to 4L. I hope this is clear. Is it clear? Is it correct? Now let's work for the second question. It is something like this. So this is the situation. This is L, this is L, and as I know that now mutual inductance is equals to self inductance, so this L effective current is passing through this. So the L effective would be equals to, this is equals to L1 plus L2 minus of 2 into M. So this will be equals to 2 into L minus of 2 into M. This is equals to 2 into L minus of 2 into L. This is equals to 0. This is L effective. I hope you got this. Have you got this? Have you? Are you sure? So now series parallel would definitely, would it be done? Are you sure? Can you do this? Can you? Are you sure? Can it be done? Can it be done? Are you sure? Correct. Now let's work for the second pattern of question for mutual inductance. Suppose the question is something like this. Let's suppose uh, one of the circular loop is there, and this loop is having radius r, and in this circle, in this circle a second loop has been passed, and what we understand is, let's suppose a current has been passed through this, and the radius of this loop, the radius of the inner loop is small r. So what the question is, question says that find mutual inductance linked to the smaller coil. Find out mutual inductance linked to the smaller coil. This is the question. So when I write M, I must understand this is phi by I. When I write phi, I must understand it's a B into A divided by I. When I write area, when I write area, I must understand this is area of smaller coil. This is the area of smaller coil for always. When I write A, this is the area of the smaller coil. You need to take an area of smaller coil each time, every time, without having any doubts in your mind. Even though if current has been passed through the smaller coil, you are going to take an area of smaller coil because it is basically an intersecting area. It is an area which is common to both. I hope you got this. Have you? Correct. So now let's write down the magnetic field due to this. This is equals to mu naught I by 2r, that we have understand and we have learned this in the moving charge and magnetism unit number 4. This is equals to mu naught I by 2r multiplied by area, that is equals to pi into r square divided by I. So this I and I has been gone, and this is equals to mu naught into pi r square divided by 2r. This is mutual inductance M Henry. I hope this is clear. Have you got this? Have you? Do you understand this completely? Have you understood this? Have you? Any doubts? Is there anything? Is there anything? No? Great. Now let's work for the next question. The question is something like this. Let's suppose it is a circular coil of radius r at its axis, and this is at distance x. A smaller coil has been placed, and this is of radius r. This is of radius r. So the question is find mutual inductance. Let's suppose current has been passed through this. Find mutual inductance linked with coil of radius r. So how will I do this? A same process. I need to write it's an m is equals to phi by I. When I write phi, I need to write b dot a by I. When I write b, it is the magnetic field due to this at this location. So I will write it's a mu naught I. It's a mu naught IR square upon 2 into bracket r square plus x square to the power 3 by 2 multiplied by area. The area would be of always of a smaller side, divide by I. So this I and this I has been gone, and I have been left with the remaining terms. That would be mu naught r square multiplied by pi multiplied by r square divide by 2 into bracket r square plus x square to the power 3 by 2. This is the mutual inductance M. I hope this is clear. Is it clear? Is it any doubts up till now? Is there anything? Is there? No? Great.